Hello friends, today I am going to explain you transition capacitance. Transition capacitance. Generally, the capacitance in suppose a diode because when you combine the p-type and n-type material, it forms the junction. Okay, the junction is established like capacitance. Means one side positive, another side negative. That is nothing but positive negative means we can say the junction acting as a capacitance. Okay, so that capacitance based on the bias voltage, that capacitance width increases and decreases. Okay, so if you apply the forward bias, the capacitance width will be decreased. But in case of reverse bias, capacitance width increases. Okay, because of unlike charges attract each other. So when we apply the bias voltage, okay, the capacitor reactance decreases between the two plates. Okay, the capacitor width increases. Okay, capacitance decreases. Okay, capacitance is decreases. The width, when width increases, capacitance will be decreases. Okay, so this is this junction capacitance, transition capacitance we can occur in suppose we can see in reverse bias. Okay, so when you apply the reverse bias in PN junction diode, your capacitor junction width will be increases, so that is called transition capacitance. Transition capacitance generally occurs in reverse bias only. Okay, so diffusion capacitance occurs in suppose forward bias. Okay, because the charge carrier is diffusing, means one side to another side, charge carrier is moving from P region to N region and N region to P region. Okay, that's why we are saying when you suppose apply the forward bias, the capacitor, the charge carrier diffuses. Okay, the charge carrier uh, ripples. Okay, diffuse to the one side to another side. Okay, that is nothing but penetrated. They penetrated from suppose after junction voltage, crossing the junction voltage, charge carrier moves from the one region to another region. Okay, so generally transition capacitance occur in reverse bias, and diffusion capacitance occur in forward bias. Okay, so if you see the diffusion capacitance with respect to applied voltage, how the capacitance transition, okay, how the capacitance increases decreases when you apply the suppose a bias voltage. Okay, reverse bias. If you see the topic transition capacitance. Okay, transition capacitance. Okay, this side the p side and this side the n side. So see here, in inside there is the donor ions will be there, and the p side acceptor ions will be there. Okay, n region is consider here, n region is a heavily doped diode, heavily doped region, and p region is a lightly doped region here. Observe, n region is n side heavily doped region, so the donor ions more compared to the acceptor ions. Okay, and p side is lightly doped region. P side is lightly doped region. Assume here p side is lightly doped region, and n side is the heavily doped region. Okay, and we are seeing now this one is one region and this one is the another region. Okay, so it form the junction. Okay, so when the suppose the distance we are representing with x. Okay, and this one is the donor ions, and this side acceptor ions. So here compared to donor ion, acceptor ions width is less. Okay, and suppose means it's a heavily doped, so this space will be decreases. Okay, this space is decreases, right? So this side ions are acceptor ions, and this side is donor ions. Okay, the width from the junction to this p region w only, this p region width is suppose we are representing you wp. Okay, and here the conductivity, suppose p region, movement of charge and acceptor ions, the total width w is equal to this p region width plus n region width. Compared to p region, N region width is high, so we can neglect the suppose P region width. So we can write omega is equal to omega P, for suppose. Sorry, this one is omega N. Okay, we are considering here omega P. Omega P, the width of this one P region more. So compared to this one, so we can neglect the width of N region. So we can write width. Suppose we can take the width, P region width we are taking. So general formula for capacitance. General formula for capacitance, C is equal to Q by V. C is equal to Q by V. We know that this is a general formula. Okay. So if you see capacitance, okay, the changing capacitance, so we can write with respect to voltage. Okay. So we know the electrical neutrality principle. Okay. So this side charge carrier is equal to this side charge carriers. Okay. Means acceptor ions equal to suppose P region charge carriers equal to N region. Okay, so we can write a neutrality principle equation and resistivity and width of P region and suppose acceptor ions, resistivity, width of P region and acceptor ions. By electrical neutrality principle equation, we can write the resistivity and acceptor ions width of P region equal to resistivity ions width of N region. Okay. So if acceptor ions much less than donor ions, then we can write width of P region much greater than the width of N region. Hence neglect the N region width. So okay. See here, if you neglect the donor ions width, by applying Poisson law, we can relate the voltage and resistivity. So Poisson law equation we know d square v by dx square. So the formula for this one, resistivity by epsilon, and substitute this resistivity formula from this. We can substitute here. Finally, apply the integration above equation. You will get 2 times you have to apply integration. You will get the V is equal to resistivity acceptor ions by epsilon x square by 2. At x is equal to omega p, width of P region or width of P region, and if you substitute the V is equal to VB, you will get the, suppose you can write in place of x omega p and in place of V you can write bias potential. VB is nothing but applied bias voltage, potential voltage suppose. Okay, so consider the volume charge of P region only. Consider the volume charge of P region only. Q is equal to resistivity epsilon area and width. So apply the differentiation. You will get the, suppose with to the this width. So this equation will come. Okay. Then after that, from the first equation, VB is equal to E into acceptor ions in P region by 2 into epsilon omega square. From the, if you write width is equal to 2 epsilon VB by resistivity and resistivity into acceptor ions. If you do the differentiation with respect to V, square root of 2 epsilon by resistivity into acceptor ions. So root x derivative. So we will get this one. So 1 by 2 square root of 2 epsilon by rho acceptor ions resistivity to acceptor ions. So in place of Vb substitute the Vb value. So we will get this one. So after that finally if you simplify this one you will get the E resistivity acceptor ions width. From that width if you write in place of from the second equation dq by dv is equal to this one resistivity acceptor ions area and the differentiation of width. So substitute here and you will get the finally the transition capacitance equation. Transition capacitance equation Ct is equal to epsilon A by width. Okay, if width increases transition capacitance decreases. If width decreases transition capacitance more. Okay, so when the junction width increases transition of capacitance value will be decreases. Okay, if width is less capacitance value is high. Okay, so Ct inversely proportional to suppose this junction width. Okay, so here this epsilon is equal to permittivity. Epsilon is equal to epsilon naught into ER and the area of the width, the W is equal to width of the depletion layer. So only thing is when you are applying forward bias, because of unlike charges the junction width is increases. Okay, junction width will be suppose increases. So when junction width increases the capacitance decreases. Okay, that is we derived the equation here. So transition capacitance is equal to permittivity this epsilon A by width W. Okay, so this is the equation. In most of the books directly they given this equation. If you note down this one, very easy to understand this concept. Okay, thank you.